Okay, so I'm going to be talking a lot about this Fraser River Delta plume right here, and this is in the Strait of Georgia. This plume is being the Strait of Georgia, so I'm looking at how the sediment from the river plume is settling down onto the delta slope and what happens from there. So what exactly are sediment density flows? These are underwater flows of sediment driven by excess density provided by their sediment load. They are one of the most important processes on Earth for moving sediment. However, relatively little is known about them. This is because they are difficult to monitor. They happen in relatively inaccessible locations. They are unpredictable occurrences as of now, and they have the ability to destroy monitoring equipment, which we will see in later slides. There has been a categorization of these flows, with the main being between oceanic flows and freshwater flows. These categorizations are based on things such as sediment source, distance of flows, and concentration. I'll be looking at flows associated with river-fed systems, and this river-fed system is the Fraser River in British Columbia, Canada. So the data for the study comes from the Victoria Experimental Network Under the Sea, or commonly known as Venus. Here is the network, one part in the Saanich Inlet and the rest in the Strait of Georgia. So this is a cabled ocean observatory located in the South Sea that provides real-time data from a variety of instruments on different platforms. This data is free and available to the public through Ocean Networks Canada, which makes it really great for studying a variety of marine science studies. So the platform being utilized in this study is the yellow star. That is the Delta Dynamics Laboratory, and so that is on the map, and then that's where it's located on the delta slope. So this right map here is of the delta structure in the Fraser River. We have the delta plain, where the majority of Vancouver sits. Then you have the tidal flats, and finally the delta slope. And so I will be talking mainly about the, delta slope. So it is important to note that our study site is near the river mouth, but is not in the actual channel. It's on the unchanneled slope. Average slope angles are about 1 to 3 degrees with local gradients of 24 degrees, and this slope extends from a depth of 2 meters to the basin floor, which is around 200 to 300 meters. This is a picture of the Delta Dynamics Laboratory. It has been deployed since 2008, where it started at a 40-meter depth, and since 2011, it is at 110-meter depth. There are a variety of instruments on this platform, and it changes throughout the years, but what I'm mainly looking at is the ADCP for acoustic backscatter, Wet Labs optical backscatter, and ADCP parascientific pressure sensor, and Seabird CTD for pressure and tides for the corresponding years. So why am I looking at this data? First noted by my supervisor, Phil Hill, was local mythology on this delta slope. So the sediment waves here are seen on the delta slope. These are not likely to be generated by tidal currents because the predominant tidal current directions on the delta slope are along slope. But the process causing upslope migration must be strong and frequent enough to make the cross-slope bed forms predominant over the along-slope forms found elsewhere on the slope. Sediment waves are commonly observed in deep-sea channel and fan settings, where they are attributed to deposition from turbidity currents. So the sediment waves here are also seen in this plot. They migrate upslope, and they migrate up current, observed to migrate in the upcurrent direction with respect to the inferred turbidity currents, which is seen there, and is likely the sediment waves on this part of the delta slope are generated by unchanneled turbidity currents. There's also been recorded events from the Venus platform, a paper published on 3 events that happened in 2008, and so this would be at the 40-meter depth platform. Evidence for these events came from low salinity anomalies, and these low salinities were brought down to the delta bottom in a proposed density flow events. A more interesting event, or a more recent event, is the 2012 event. So on June 4th, 2012, the Delta Dynamics Laboratory lost connection. So in the moments before losing connections, it seems to have tumbling downhill and collecting data before the cable finally severed, and it was found later downslope and buried by sediments. Gwyn Lintern of the Geological Survey of Canada believes this event was moved by a density flow event, and more details are currently being prepared for a paper. While it was tumbling, it was taking data at different angles, so that is more to be discussed later. So my study is aimed to understand the conditions at which unchanneled turbidity currents are triggered, and are there any similar conditions between these 2008 events and this 2012 events, because the data was being recorded at 2 different depths during these times. So my trigger mechanism, studying conditions at which these events are observed, and the conditions I'm looking at for the 3 events in 2008 and the 1 event in 2012 is similarities in river discharge, sediment settling events, both in duration and the ADCP backscatter intensity, and finally the tidal excursions during those times. So here is a plot of the Fraser River discharge, annual 2008 on the top and 2012 on the bottom. The red arrows are the days in which the 4 events took place, the 3 in 2008 and the 1 in 2012. It can be seen that both of these events took place near or at high discharge for the year. And this discharge is during the freshet period, which is caused by snowmelt, and also has a large sediment loads because of this. It is noted that while 2012 does not appear at or after the peak discharge, it still occurs after a period of higher discharge. 2012 is a quite odd year in that the peak discharge doesn't occur till late June, which usually the peak discharge looks more like 2008. So here we have a time series of the ADCP backscatter, and the top 3 are 2008 at 40 meters depth, and the bottom is 2012 at 110 meters depth. So time series, this is the water column passing over the sensor. So these black boxes here show the sediment settling events that I'm talking about. So during ebb tide, the river plume comes over the sensor and sediment begins to be deposited to the delta slope. And it can see that there's this buildup of concentration at the bottom. The red arrows, again, show the start of the events. In the top 3, 2008, these events lasted for about 6 to 9 hours. It's not quite known how long it lasted in 2012 because basically right here, we lost the platform. So all days in which these events occur, there was a significant sediment settling event down through the water column during the ebb tide prior to the event. These are the same time series as seen in the previous slide, and here we were looking at the duration of the event, of the sediment settling event. So how long was the sediment settling from the river plume down to the delta bottom? And for the respective data sets, so for 2008 data set and 2012, these durations for these particular days were greater than average by 0.2 to 1.5 hours. So these are the larger of the sediment settling events that occur. Next, we have tidal exchanges. So these are plot series, time series of tidal height. The freshet data set, once again, because we lost the platform, is much shorter in 2012. So unfortunately, we lost the rest of the data for that year. Again, the red arrows occur, or when the density flow events occurred. So all of these events occurred during this high spring tide period, where the tidal is moving more and possibly allowing more sediment to settle on the delta slope. Next, we have ADCP backscatter intensity. So these are, again, a plot series of the daily maximum ADCP backscatter intensity that happened during the sediment settling events. And these are taken at 3 depths for both 2008 and 2012, and these depths were near bottom, mid column, and near top. This intensity goes in cycles, kind of similar to what we saw in the tidal height, and it suggests a correlation with that tidal height. And again, our high intensity suggests higher concentrations, although this hasn't been calibrated directly. One of my last bits of analysis was looking at apparent settling rate and grain size from this backscatter. So this is the June 4th, 2012, the infamous day right before the platform was lost. So this is a color adjusted image, and we can start looking at the structure inside the sediment settling plume. So settling rates are estimated from the surface plume to the seafloor bed by drawing a line that tries to capture the slope happening there. For this plot, this would give a settling rate of approximately 1.13 centimeters per second. And applying Stokes' law, this would be the equivalent of fine sand. The actual grain size seen on the slope is from fine sand to silt. So we are getting slightly higher settling rates due to a rapid settling mechanism that's probably non-Stokesian. Especially since we can see a higher settling rate here that's brought out when you adjust the color contrast of this image. So as the surface plume moves over the sensor, we are seeing different settling rates happening, and more is to be looked in about that. Another interesting occurrence is these little finger-like settling that possibly resembles convective settling that has been seen in laboratory studies. So that's something interesting that you sometimes see when you adjust the color on these images. So in conclusion, all of these density flow events occur during high river discharge, high tidal exchange, and high backscatter intensity, so inferred high sediment concentrations. The distinct sediment settling events are observed for each of these events. These occur during the ebb tide when the surface river plume moves across the delta slope. Sediments observed falling out from the surface plume, and they seem to concentrate in the near bottom layer. And then the structure in plume suggests convective settling may enhance the settling rate and help build the concentration. Thank you.